In this video, you will learn how to use the Breeden-Litzenberger formula to derive the risk-neutral probability density functions from option prices. This can be extremely useful because actual computing of option prices can be a time and computationally intensive task, especially when you have something that you're trying to do very complex dynamics of and when there is very high dimensionality. The beauty of the Breeden-Litzenberger formula is that we can actually just compute this complicated derivatives once at different strikes for a particular tau, so time to maturity, and we can get this risk-neutral probability distribution function and be able to calculate a whole bunch of complex derivatives extremely simply and quickly. So once we've got a discrete PDF, what we're going to do is we're going to actually use linear regression to be able to smooth out this function. Then we're going to use we're going to create the cumulative density function, and then we're going to be able to price all sorts of complex derivatives easily using this risk-neutral distribution that we've defined for a particular time. First off, what is it? Well, the Feynman-Nack analysis enables us to define the risk-neutral probability in which we can price options. So we're going to let this function in terms of the risk-neutral probability measure Q of ST denote the terminal risk-neutral, so the Q under the Q measure, probability at time t. And we're going to let this F risk-neutral probability Q denote the cumulative probability distribution function. So a European call option at time little t expiring at big T with strike K is priced as follows. So here we're using tau to represent that time to maturity. So here we've got our call price in terms of K and tau, and we've got the risk-neutral discounted expectation of our payoff. So here we can expand that using the indicator function, and we can get that this discounted integral between K and infinity of ST minus K times by the probability distribution function, this risk-neutral density function in terms of our risk-neutral measure. So how can we actually calculate directly from this formula? Well, we're going to get into that. So now that we have this formula in terms of K and tau, in the case where the risk-neutral density function is log normal density and volatility is constant with respect to K, then this yields the Black-Scholes formula. So under the basic no arbitrage restrictions, we can consider more general densities than just this log normal distribution of the underlying. So here we can use the Breeden-Litzenberger formula from 1978 to show that the first derivative is a function of the cumulative distribution function. So here what we mean is if we take the first derivative with respect to K of this integral here, then we actually get minus this exponential discount factor times by 1 minus the cumulative density function. So the second derivative then extracts the PDF. So if you then take the second derivative with respect to the strike, centered around K equals ST, then what you get is the discount factor multiplied by this risk-neutral PDF. Now, thanks to Bruce Meiserak in chapter 35 for putting a lot of this information together in a very easy format to understand. I recommend going to this link in the description, and he's written a whole bunch of things on estimating applied probabilities from options prices and underlying. Great resource there. So for Python, let's go and see how we can actually apply this bit to actually get this risk-neutral distribution. So here we're going to have NumPy, we've got SciPy, Pandas, SciPy we need to import stats explicitly, and then we're going to use matplotlib. Now, let's look at what we're going to be pricing today. We've got a European call option with stochastic volatility. Stochastic volatility is going to be under the Hester model. So our risk-neutral dynamics for the underlying process, here we've got our drift and our diffusion term that we're used to seeing. Now here, the variance, this square root variance process is going to be modeled with this SDE, which of course you'll recognize from the Hester model, and we have previous videos on the dynamics of this. Now here we've got a correlation P, just that is the correlation between these two Wiener processes, between the variance process and then the stock underlying process. So let's initialize our parameters. Here we've got a stock price of 100, strike of 150, tau is 1, and then an annual risk-free rate of 6%. Heston-dependent models, who cares? You could take this from market data. We've done that before, using machine learning techniques under the risk-neutral measure to be able to find what these factors are. Go and take a look at that video if you're interested in that process. Here I'm just defining kappa is 3, which is the rate of mean reversion. We've got theta, which is the long-term variance. So I've just got this volatilities of 20% long-term, and then we've got the initial volatility, which is 20%. And again, variance, so we're squaring these numbers. And here we've got rho, which is the correlation between returns and variances. I wanted a really skewed risk-neutral distribution. I don't want a log-normal distribution, so I've made this positive 0.98. So that'll show an interesting effect on our risk-neutral distribution. And here we've got sigma, which is the volatility of volatility, which is this factor here. So here I've called that 20%. Now the risk premium of variance, I'm just saying that that's already been taken into account with the variable, the developed variable that I've defined here in my kappa. So I've just called it 0 for now. Now, one thing that you need to understand with the Heston model is that you can get negative volatility if this condition is not satisfied. If 2 times kappa times theta is not greater than sigma squared, then you're going to have issues. But here I've convinced myself that this condition holds, so I'm not worried even if I discretize. Now, the Breeden-Litzenberger formula, here let's determine the risk-neutral probability distribution function. So as we've said before, it's that discounted factor. So here, remember that we had that our second order derivative was equal to the discount factor times by the PDF. I've just taken that discount factor and now we've got the forward factor multiplied by this second order derivative. Now, in order to approximate that derivative, we're going to use finite difference approximation. So in actuality, what that looks like is we're going to get our call prices for different strikes, and then we're going to make sure that these strikes have an even difference in between them, and we're going to use this formula that is centered around a particular strike to be able to calculate our risk-neutral distribution for that particular strike at that time to maturity. We're just going to be defining a 2D PDF here for a particular time to maturity. Now, for actually calculating option prices under the Heston model, what we've got is an analytical solution, and that is in terms of the characteristic equation and Heston model that we have here. Please look at a previous video that I've got linked up on the screen right now, where we've actually taken you through how to calculate this from the characteristic function. So essentially it's a two-parter. Here I need to be calculating complex integrals on this domain from 0 to infinity of this characteristic function. Now here I've defined what that characteristic function is, and then I need to compute that complex integration, and the way that I'm doing that is through rectangular integration. So here I step through my domain size from 0 to infinity, but you don't need to go that far for option pricing. I've just gone to 100 here, and we're going to take 650 segments. Now it's really important because with our complex integration here, the step size that you choose will really impact, especially for out of the money options, will really impact your precision of calculation. And the reason is that Python has this terrible round off issue because it stores things in terms of binary variables. It's decimals in terms of binary variables. We will talk about that later, and why the quantlib that's implemented in C is much more effective at completing this numerical integration. Anyway, we can implement this, this equation, and we're going to take the real component of the option price as we've defined in the formula up here. So we have an analytical solution, semi-analytical solution. We still need to compute this, this numerically across this using rectangular integration. So for a whole bunch of strikes, I'm going to take 60 through to 180 with a step of 1. I'm going to calculate my option prices of the Heston price using rectangular integration. I've defined all my variables as above. So once we've calculated these option prices under the Heston model, then we're going to use second order finite difference approximation to actually calculate the risk neutral distribution and the curvature. So here, you'll note that we have this risk neutral distribution as that forward factor times by our second order finite difference approximation. So let's actually just place that within a data frame, our strike and our option prices that we have above, and then we're going to use the shift function to get the strike price above and the strike price below. So here we've got -2 of the current call option prices, so 2 times that price here. Then we've got plus the next strike above, so we just use the shift by 1 function in Pandas data frame, and we're going to add the shift price -1, so the strike below. Then we're going to divide that whole summation through by the step size squared that we took, and the step size, of course, was just 1 strike. So we did that by definition when we defined and calculated our option prices. So let's plot what that looks like and what that curvature looks like. So here we have our Heston stochastic volatility calculated option prices, and that's in the blue. And then here we've got our curvature on the y-axis, which is really the density function. Now here I haven't taken the forward factor, so it's approximately the PDF here, and we'll do that in the next step. But see here, we've got some issues because on the left-hand side, you can see here how the curvature actually dips below 0. So we have a density that's below 0. So obviously that doesn't hold, and therefore this is just impactful by the round off errors as you get out of the money. The calculation with our rectangular integration function does not do so well. So let's compare this with the QuantLib Heston model. So here we've taken a lot of this code from Quant Stack Exchange on this question here, which is computing the probability density function of the Heston model. Go figure. I haven't used QuantLib a lot, but obviously I think it would be good going forward to actually benchmark a lot of the models that we're implementing here in Python with the QuantLib library. So here you have to define your date ranges of the product that you're actually valuing, setting up your discount curve, and you've got a flat curve and then a yield curve. Then you need to have a Heston model, so you define your Heston process with all the factors that we have identified above. So your spot price, and then your initial volatility, kappa, theta, sigma, and rho. And then you create the model from the process. You have this Heston handle, model handle class, and then that goes into creating your Heston black vol surface. Now from that we can use the .black vol function for a particular time to maturity and a particular strike K. So once we've got our vols, we can then use that to calculate the correct Heston pricing method given the Heston analytical engine. So once we've got the Heston prices, we just append that as the discounted expectation of those prices, and then we can add that into our Pandas data frame. So let's compare our rectangular integration with our quant library. So here you can see we're actually just calculating that exact same graph as before. We have call prices in blue on the main axis, and then on the second y-axis here, we've got that density. And the difference is you can see that the density has not dropped below 0, which is ideal for a probability density function. So obviously we're going to go with this one. Now, what are the differences and why? So to look at the differences, we can first look at the MSE. We can look at the mean of the difference of the option prices from our rectangular integration to the QuantLib library. MSE is very small across all these strikes, 0.07, and you can see only small differences here between at all these strikes. Now it does get larger, especially when you get out of the money further and further. And the reason for that is we have a large Now, the main reason for the difference is because of a result of the complex integration over really small increments. Now, Python has big issues with round-off errors at small values approximated because of the binary float point numbers. Because Python actually approximates these decimal values by binary float point numbers, we get rounding errors. And I've put 2 links there that you can investigate to see why that is the fact. QuantLib is obviously more effective at this. It's actually been implemented in C and handles decimal points a different way within their calculation. So they've got a slightly better numerical integration scheme than our Year 12 rectangular integration. I would love to hear your solutions for Python in how we can actually get this numerical integration a little bit better and then more precise, maybe taking different step size functions, making that variable for different strikes. I would love to hear your suggestions in the comment section below. How can I improve my rectangular integration function? So now what we've got a discretized approximate PDF. So I want to take those prices, that curvature, and I'm going to multiply it by our forward factor now. So I've got our forward factor multiplied by the curvature array, and what I want to do is I want to use SciPy interpolate, and I'm going to interpolate between the strikes. So given a strike, I want to be able to interpolate our discrete curvature function. So I want a PDF, given the strike, I'm going to get back the curvature. So I'm going to use 2 different types of PDFs. So I'm going to use 2 different types of interpolation. I'm going to use linear and cubic, and we're going to look at the difference between the 2. Now, really important here, SciPy is only going to be able to then compute the strikes. So once we've actually created this interpolation method, we can only actually calculate on between the interval of the data that we've given it. So we gave it strikes between 60 and 180. So we can only calculate strikes between those. So I've gotten from 61 to 179. And here we've got the PDF using the cubic and then PDF using the linear function. So as you can see, our forward multiplied by the curvature has given these really nice PDFs, of which cubic and linear, I'm not seeing much of a difference. Perhaps it would have made a difference if we took larger step sizes in our strikes. And of course, you might be limited if you're using market data to imply this directly, but here I'm pretty comfortable with the linear interpolation that we've got here. So how can I get the cumulative distribution function of this risk-neutral density function? Well, essentially what I'm going to do is I'm going to take the cumulative sum of the PDF. So I've got the PDF linear of all the strikes. I'm taking the cumulative sum of the PDF, which is in fact the CDF, but that's the discrete CDF for each particular strike. And again, I'm just going to use a linear function using SciPy interpolate interpret p one-dimensional. So here we've got our CDF, and now I'm going to plot across all those strikes, and we're going to look at what that looks like. So here we've got our CDF of our risk-neutral distribution at a particular time to maturity, so tau, and you can plug in a k and you get the probability back. So how do we actually use the risk-neutral PDFs to price complex derivatives? So remember here that this risk-neutral density function is defined at a particular time to maturity, time to expiry, tau. At this point, it's extremely model independent. We have a risk-neutral density function at a particular time to maturity that has either taken in market prices or taken in a particular model, like we've used the Heston model. And now we can use that risk-neutral density function with those particular parameters, etc., all embedded within this PDF. What do I mean by that? Well, I'll show you. Here we've got a generic pricing formula for just a call and a put, and this is in terms of K and tau. So now I can just complete this numerical integration of this PDF, our risk-neutral PDF for a particular tau. of my call payoff, which is just st minus k between k to infinity, or for a put, it's the interval minus infinity to k of k minus st. Now, I'm going to do both of those. So here we've got we're defining our integrand, which is just in terms of x, so our stock price, and then we've got an argument k. So here we're returning our stock price minus k times by our risk neutral PDF. Now we've got our integrand of our put, which is just the opposite. We've got k minus x. Now our integral for the call is defined on the interval from k to infinity, but of course we can't go to infinity. Our maximum CDF that we can calculate because of our interpolation is to 180. So here I've just gone 178. And then, of course, then we've got our integrand between k and 178. I've limited it to 1000, and then I've got my argument of k being fed into that integrand function. I'm then going to compute for each k in our strikes the put using the same integrand, but our interval is going to be from minus infinity. Again, our lowest defined range, which is essentially 0, as we can see from our CDF. I've got 61, and then I'm going to k. So here now I've got the discount factor multiplied by our integral, and then I've done the same for the put. So we can append those values, and then we can display them in a pandas data frame. And here I'm just showing you how we've been able to price both puts and calls for different strikes as easily as that. And if it was really high dimensions, we had high time steps, it takes high complexity to be able to calculate this, whether it's model dependent, actually pricing things off the risk neutral density functions is very, very efficient. So I would encourage you to go out and try and derive risk neutral density functions for whatever you're interested in. In one of the next videos, we're going to look at how we can actually take market prices and do model independent risk neutral density functions from the market implied prices. So thank you very much for listening. Until next time, YouTube, see you later.